In just 6 weeks, NASA will send 4 humans through a region of space that damages DNA, destroys electronics, and shortens human lifespans. For the first time since 1972, astronauts are leaving Earth's protective shield. They won't just travel farther than anyone has in over half a century. They'll pass directly through invisible zones of radiation powerful enough to permanently harm the human body. This mission is called Artemis II, and it isn't dangerous because of rockets, it's dangerous because of radiation. The question is no longer whether we can reach the moon, it's whether modern technology can truly protect humans on the way there. Since the end of the Apollo program, every astronaut you've ever seen has stayed close to Earth. The International Space Station, space shuttle missions, private space flights, all of them orbit safely inside Earth's magnetic shield. That shield is invisible, but it's powerful. It deflects most of the dangerous radiation, constantly pouring in from the sun and deep space. Inside it, astronauts are protected. Outside it, space becomes hostile very quickly. Artemis II changes that. This mission will carry 4 astronauts farther from Earth than any human has traveled in over 50 years. They will orbit the moon, test critical systems, and return home. But before they ever reach the moon, they must pass through one of the most dangerous radiation regions near Earth. And that's where the real risk begins. Surrounding Earth are massive rings of trapped radiation known as the Van Allen radiation belts. They were discovered in 1958 and exist because Earth's magnetic field captures charged particles from space and holds them in place. There are 2 main belts. The inner belt is packed with high-energy protons. The outer belt is filled with fast-moving electrons. Together, they form invisible radiation zones capable of damaging cells, interfering with electronics, and increasing long-term cancer risk. Satellites pass through them quickly. Astronauts usually avoid them entirely. During the Apollo missions, astronauts crossed these belts by following carefully planned paths and minimizing time inside them. They didn't linger. They passed through as fast as possible. That was more than 50 years ago. Now Artemis II is about to do it again, but with a very different spacecraft and a very different future in mind. Radiation in space doesn't behave like radiation on Earth. There's no atmosphere to soften it, no magnetic field once you leave Earth's protective zone. Radiation comes from 3 main sources: solar particle events from the Sun, galactic cosmic rays from exploding stars across the galaxy, and trapped radiation like the Van Allen belts. Some particles pass straight through metal, some damage DNA directly, others quietly accumulate in the body over time. The danger isn't instant death, it's cumulative damage. A short exposure might be survivable. Repeated exposure increases long-term risks: cancer, neurological damage, vision loss, and cellular changes that can't be reversed. That's why Artemis II matters. Because this mission isn't just about reaching the moon, it's about proving humans can survive the journey safely. NASA's answer to this challenge is the Orion spacecraft. Orion is built specifically for deep space, not low Earth orbit. It's designed for longer missions, harsher environments, and higher radiation exposure. Its structure includes radiation-resistant materials. Its electronics are hardened to survive high-energy particles. Its flight path through the radiation belts is carefully planned to minimize exposure time. NASA expects the crew to pass through the Van Allen belts in just a few hours, fast enough to keep radiation doses within accepted safety limits. Inside the capsule, radiation sensors will measure exposure in real time. Mission control will know exactly what the crew is experiencing. On paper, it sounds reassuring, but space doesn't always follow the plan. The biggest unknown isn't Earth's radiation belts, it's the Sun. The Sun goes through cycles of activity. Right now, it's approaching a solar maximum, a period marked by increased solar flares and energetic particle storms. A strong solar storm at the wrong moment could dramatically increase radiation exposure. Even modern shielding has limits. During the Apollo era, astronauts crossed the radiation belt safely, not because radiation wasn't dangerous, but because no major solar storms happened at the wrong time. That wasn't engineering. That was luck. NASA now monitors the Sun constantly. Artemis II launch windows are chosen to reduce solar risk, but solar activity can change with little warning. That uncertainty is part of the gamble. Artemis II is not just another spaceflight, it's a turning point. What happens here will shape everything NASA does next. This mission is a full-scale test of whether humans can safely travel beyond Earth's protective shield again. The goal isn't a single visit to the Moon, it's repeated missions, long-term presence, and eventually the journey to Mars. Mars changes everything. A Mars mission would expose astronauts to deep space radiation for months, not hours. There's no quick dash through danger, no fast return home. Astronauts would live outside Earth's magnetic protection while radiation slowly accumulates in their bodies. If Orion cannot protect astronauts during a relatively short pass through the radiation belts, then the risks of longer missions become far more serious. Shielding designs, flight paths, radiation models, mission timelines, all of them depend on this test. Artemis II answers one critical question. Can modern engineering truly protect humans beyond Earth orbit? There are 4 people on this mission. Not robots, not test dummies. They know the risks. They've trained for years. They trust the science, the engineering, and the teams behind them. But this is still exploration, and exploration always carries uncertainty. Every major leap in spaceflight history came with doubt. Mercury, Gemini, Apollo. Artemis II belongs to that same lineage. If Artemis II succeeds, it proves something powerful. That humans can safely leave Earth orbit again. That radiation risks can be managed with modern technology. That returning to the Moon is not nostalgia, it's preparation. It opens the door to Artemis III, lunar landings, long-term missions, and eventually Mars. All of that depends on getting this right. There won't be explosions. No dramatic moments visible to the eye. Radiation is silent. That's what makes it dangerous. The success of Artemis II may look boring on the surface. A clean launch, a smooth lunar flyby, a safe return. But behind that simplicity is one of the most complex risk calculations NASA has ever made. And the future of human deep space travel rests on it. In 6 weeks, 4 humans will cross a boundary we haven't crossed in decades. They will pass through invisible danger, trusting that preparation is stronger than uncertainty. Artemis II is not about bravery. It's about biology versus ambition, and this mission will tell us which one wins. If you want more deep dives into space missions, hidden risks, and the technology shaping humanity's future beyond Earth, make sure to like this video. Subscribe to the channel for more stories like this every week. And comment below, do you think Artemis II is a bold step forward, or a risk we're underestimating? Your support helps this channel grow, and it helps keep space exploration stories alive.